In this video, we're going to talk about what a probability model is and how to use a probability model to solve problems in statistics. Before we get into the examples, I want us to pay particular attention to these four rules over here. When we talk about probability, these four rules apply always. So number one, any probability is a number between 0 and 1. Think in terms of a percentage. Any percentage can take on any value from 0% to 100%. The same applies for probability, has to go anywhere from 0 to 1 inclusive. For part B, all possible outcomes together must have a probability of 1. Part B is what we are going to model in both of these examples. Another way to think about it is the weather for today. Could be sunny, it could rain. We're going to use just those two examples. And the probability that it's sunny, let's say, is maybe 42% or 0.42, then the probability it rains has to add up to 1, okay, or 0.58 or 58%. So all outcomes possibly together have to equal 1 or 100%. Part C, the probability that an event does not occur is 1 minus the probability that the event does occur. That makes sense. We're talking in terms of a baseball game where there's no ties. It's either you win or you lose. If the probability that I win the game is 0.45 or I have a 45% chance of winning the game, 1 minus 0.45 gives me 0.55. So the probability of me losing the game is 55% or 0.55. I'm using that rule of 1 minus to figure that percentage and that likelihood out. And then the last rule, if two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. Okay, so now let's take a look at an example where we might have a tie, right? Let's say if the probability that I win is still 45%, but now the probability that I tie is 5% or 0.05. Okay, these outcomes have nothing in common, right? A win is much different from a tie. The event or the likelihood that as a player, I know I'm either going to win or tie is 45% plus 5% or 0.45 plus 0.05 to give me 0.5 or 50%. We add those together and we often will symbolize that in probability with this expression here, okay, where we see a capital P and then the event itself in parentheses. And we can show our work here, 0.45 plus 0.05 equals 0.5. So those are the four rules we're going to look at in these two examples, all right? Speaking of these examples, what do we have in terms of a probability model? Well, the format of a model is what I want to go over first. You're basically going to be given two different rows where the first row is the actual event, okay, whether you're talking about, in this case, the class, or sometimes when we look at things like expected value, we'll use the four different, we'll call them monetary options. Think, for example, the lottery, right? If we play a scratch off, there's usually more than one outcome. You could maybe win $1,000 a week for life. You might be able to win $500. You might be able to win $20. You might get your money back and win $5. Or what happens most of the time is you win $0. You don't get anything back. So in that respective probability model, you would have 5 different columns with an attached probability or an attached likelihood for each of those outcomes, okay? Let's talk in terms of the college experience, okay? You have freshmen, sophomores, juniors, and seniors. And let's say the breakdown for TCNJ is we have 28% freshmen, okay? We have 26% sophomores. We have 23% juniors. And then using this data, I wanted to figure out the likelihood or the probability of having a senior, okay? Now, before I solve this problem, I want to show you what rule that we're going to use here, okay? And it's rule part B, right? The second rule that we talked about, all possible outcomes together must have a probability of 1, all right? And indirectly, we're going to use part C. The probability that an event does not occur is 1 minus the probability that the event does occur. So how do we use that rule in this example? Well, I want you to think of the opposite of a senior, okay? Just like before we talked about win and loss, the opposite of a win is a loss. It's tough to think about the opposite of a senior, but if you're not a senior, you are either a freshman, a sophomore, or a junior. So if we can lump these probabilities together and then subtract that from 1, we will reach a probability for a senior class, okay? Or another way to think about it, I think the more direct way of interpreting this is I know I have 4 different outcomes here, okay? And I know that there's a sure chance that if I select a student at TCNJ, 100% they're going to be a freshman, a sophomore, a junior, or a senior. So I need to ensure that this value here, whatever I plug in, is going to allow this row to add up to 1 and only 1, okay? So add these up first, okay? If we do 0.28 plus 0.26 plus 0.23, we get a value of 0.77. Again, that's all of these classes added together, okay? Now, that doesn't mean a senior is 77% chance of getting a senior. It means I have to take this number now and subtract it from 1, okay? So 1 minus 0.77 will give me a probability of 0.23. So to answer our question, what's the probability that we select a senior? I would say the probability of a senior is equal to 0.23, okay? And you can always check by adding this row up, okay? And notice if you can see it really closely down here, it gives you the sum already. The sum is equal to 1. But if you don't see that, you can always just type in the sum of this row, and we get is equal to 1. So we're in good shape, okay? So our answer for that one, again, let's highlight it here, is going to be equal to 0.3, all right? Let's take a look at example number 2, all right? Let's change the scenario a little bit. Let's say we're still studying, we'll say students at TCNJ, and we're changing the variable of interest here. Now we're talking about the number of siblings that students at TCNJ have, okay? They don't have to go to TCNJ, they can go anywhere. And let's say our model and our survey gives us this breakdown, okay? So 25% of our student body is an only child. Okay, I'd be curious to see if that's actually the breakdown. It seems a little high to me, but that's the number we're going to use. 37% of us, or 0.37, has 1 sibling, and then 27%, or 0.27, has 2 siblings. Okay, and then we just lump everybody else in the same category of 3 or more. All right, so let's, just like the previous example, figure out the probability we select a student with 3 or more siblings. Okay, so rule number 1, or step number 1, let's add these 3 together first. So we're going to do 0.25 plus 0.37 plus 0.27. And we get an answer of 0.89. And then 1 minus that will give us 0.11. And again, you can always check your work. If I highlight this row, see again how I get that sum of 1. So the probability that we select a student with 3 or more siblings is not going to be a question mark. It's going to be 11%, or 0.11. Okay. Now the second question is what gets some of us at some times. And that question reads, what's the probability that we select a student with exactly 3 siblings? Okay. Well, this is a little more difficult to calculate, okay, because my probability model, if I interpret 3 or more, that leaves the options for 3 siblings, for 4 siblings, for 5 siblings, 6, 7, 8, and I'm just going to, this has a nice little rhyme, 6, 7, 8, with no way to differentiate. I know that's kind of corny, but bear with me here. I can't tell exactly what the percentage is for just 3 siblings. Okay, all I know is that these options, and more than 8, all lumped together are 11% or 0.11. So the probability for exactly 3 siblings, I might have to, I would say there is not sufficient information in this probability model to answer this question. All right. And that's a good trick question on a quiz or a test when you're evaluating probability models. Just be careful of the phrasing, because the phrasing is going to lead you to your answer. And sometimes that answer is not concrete, and that's okay.